Welcome back, AP students. Hopefully you had a nice spring break, got to a little bit, clear your mind, focus up for the remaining portion of this school year. Obviously, things are a little different than what they were. A lot of you got my email. There's a few who never responded back to me, but hopefully you'll watch this and you'll get the information. With the change of what's happened across the country, really, the AP exam has not been canceled, but it has been moved to be online. So it's going to be in a lockdown browser. It's going to be free response question, 45 minutes worth. Now, they haven't released exactly how many of them, but that's just a little bit of quick information. So that's what prompted me to send that email out last Friday, just over a week ago, to advise you all that I had canceled the one assignment that I had placed in AP Classroom, which was 9.7. All the exam is going to cover is units 1 through 7. So we are going to make a good effort to work through 1 through 7, work some example problems, and I'm going to start assigning questions from your book that you have. 5 steps to a 5, and I have the first assignment upcoming on Thursday for that. And I'll also work some problems in the book as well as we go through. The first couple units, obviously, we've worked a lot in the more advanced units we've covered, so those topics won't be overly aggressive for you, but I'm still going to work through them. I plan to do Unit 1 and Unit 2 this week. Next week, I plan to do at least 3 and possibly get into 4, because through the month of April, I want to wrap up all the units so that I can assign to you on AP Classroom some free response questions that are practice exams. That's my goal. So that's what we're going to shoot for. Once again, if you have any questions or anything, please shoot me an email. I will do my best to answer them. So let's begin on a review. So in AP Classroom, the Unit 1 review is due on Tuesday. That's tomorrow by 11:59 p.m. So the end of the day tomorrow. So you'll be able to go through this lesson today and tomorrow as a quick review, and then work on finishing up those particular questions on AP Classroom. So first off, Unit 1 was about atomic structure and properties. So first off, we begin talking about moles and molar mass. Now, we've used those a lot. I'm not going to spend a great deal of time on this, but everything you do, you basically have to go to moles first. And we know Avogadro's number is part of moles, the 6.02 times 10 to the 23rd. Please don't forget those key concepts. If you want to get the molar mass, you have to add up all of the masses. So the mass of each one of the elements that are in that particular compound. So when we talk about AMU, atomic mass unit, remember that carbon was the model element, and it was used to study isotopes. And please remember what isotopes are. It's the same element, just it has different numbers of neutrons. So you add them all up. If you're talking about, for example, magnesium chloride, you take the mass, the molar mass of magnesium, and then the molar mass of chlorine times 2, because there's 2 of them. And when you add them up, that gives you your 95.21. Please remember that the basic rule is you go to the second decimal, the 100th position when you're doing the molar mass. As it says here on the bottom, don't round to the 10th. Don't round to the 10th position. It's always to the 100th. Everyone remembers looking at these spectroscopy, mass spectroscopy of elements and determining its atomic mass. Remember what atomic mass is. Atomic mass is how much of that, it's a weighted average. It's a weighted average. How much of each isotope occurs naturally in a sample. So here we have strontium. So I have this chunk of strontium. If I were to break that down through mass spectroscopy and determine the abundance of each isotope in it. This is what it would look like. So how do I calculate based on something that looks like this? Well, on the bottom here, I have my mass given. So let's just look at this. So I have a mass number of 88. So I can write over here on the side, I can write down 88. And if I follow across over here, this, if I come over here, the relative abundance, let's just say that's about 82%. So I can go times 0.82 equals. Then I come here to my next one, I have 87. So I can put down here my 87. And I'm going to look at the relative abundance of this one. So it's right about here, come over here. So I would say about a 7. So that is 7%. So 7% is 0.07. And then I have here my 86. So I come over here and write down 86, and I multiply that by its relative abundance is 10%. So I can go 0.10. And then last one over here, I have 84. Write down 84. And that is roughly about, let's just say 1%. So 0.01. So if I want to find the atomic mass, I get my calculator and I just plug these things in. So I go 88 times 0.82, and I should have roughly 72.16, 72.16. Then I can go 87 times 0.07, so I have 6.09, 6.09. Then I go 86 times 0.10, and I get 8.62, 8.60 actually. And then lastly, I have 84 times 0.01, and I get 0.84, 0.84. So now I can plug all this into my calculator. 72.16 plus 6.09 plus 8.60 plus 0.84, and I should come out to 87.69 if I add this up. 87.69, and this is AMUs or grams, because that's how we use the atomic mass. So when I look at my periodic table, which I just pulled up right here, strontium, that's what I'm looking at, it says 87.62. So look at how close I am to that 87.69 I calculated. Now, obviously, I'm guessing on some of these percent abundance. So if I would have them actually given to me, and sometimes a chart will actually give you very technical amounts, I would have been exactly spot on. So that is how you look at a graph for mass spectroscopy. Hopefully that comes back to you. We've worked quite a number of these problems previously. The next thing in Unit 1 is matter. So we know what matter is, anything that has mass and takes up place. Well, matter can be broken up into two main parts. You have pure substances and you have mixtures. So we're going to start over here with mixtures first. So you have that broken up into heterogeneous and homogeneous. So remember, heterogeneous is things of uneven mix. So sand and dirt, you got oil and water, things of that nature are heterogeneous mixtures. So when you talk about a heterogeneous mixture, you can, for the most part, easily separate them. You can filter them through filter paper. You can just pour it off, and that's called decanting. Or you could do a process called suction decanting, where you have a vacuum pump that pumps out and you can pull off different layers. That's how you get and separate a heterogeneous. You can actually also pick, if you had some substances like rocks that are in sand, you can simply pick them off. So that is another process to separate a heterogeneous mixture. Now, a homogeneous mixture is one phase. Remember, heterogeneous is said two or more phases. Homogeneous is one phase. So a homogeneous mixture is also known as a solution. Solution chemistry dealt with that. So when we talk about a homogeneous mixture, they're not as easily separated. You have to use distillation for the most part to separate a solution. And think of just salt and water. You can distill it across, or alcohol and water based on its boiling point. Remember, that's what distillation is based on, is boiling point. Another homogeneous mixture is an alloy. We didn't talk a lot about that, but please remember that that is what an alloy is two metals that are blended together. Remember, they're melted, added. It doesn't always have to be a metal. It can be non-metals that are added as well, but they're called homogeneous mixtures. Now, if we go to the other side here, pure substance, they can be broken down into compounds and elements. Remember, a pure substance, an element, is in its simplest form. It cannot be broken down any further. And the examples given here, hydrogen, oxygen, carbon, those are our elements. Now, a compound is put together in whole number ratios, and they cannot be broken down without chemical means. Now, remember, you can react them together to form other compounds, but without chemical means, you cannot break down a compound. So you can't filter it, you can't distill it, it has to be broken down chemically. So those are our pure substance and our mixture. Now we have the law of definite proportion. So remember Dalton's and Dalton's postulates. One of his postulates were that atoms can form compounds by coming together in small whole number ratios. We talk about water, for example, here. Water is 2 atoms of hydrogen to 1 atom of oxygen. So you could say it is always going to be 2 to 1. Always 2 hydrogen to 1. If you have something that is not 2 to 1, it is not water. If you have H2O2, so 2 to 2 or 1 to 1, once again, that's hydrogen peroxide and not water. We could also look at it in terms of mass, but that's the law of definite proportions. It will always be in that format, 2 to 1. Never will change. If you have something other than that, it is not water. And then there's also properties that apply to it. If you have pure water, it's boiling at 100 degrees Celsius and it's freezing and melting at 0 degrees Celsius. And that all falls under the law of definite proportions. So there are properties, and those are intensive properties and extensive properties. We talked about those previously, but let's continue on with law of definite proportion. So it also applies to mass percent, the percent by mass. So here we have ethyl alcohol, C2H6O. So we could calculate the percent by mass of that. So please remember, that is another skill of doing. So you take the mass of each element, in this case, the carbon times 2, the hydrogen times 6, and the oxygen, and you divide that number by the total mass, So that's what they're doing here. They're getting the molar mass, and then they're dividing how much of each element by that molar mass, and then that's how you get this percent. Anytime that you find a substance and you break it down, if it is anything other than this percent, 52% carbon, 13% hydrogen, 35% oxygen, if it's not that, then you do not have ethyl alcohol. You have some other substance, or it has impurities. This is also the law of definite proportions, is that it by mass percent, it'll always be the same. Now moving into atomic structure. We're pretty familiar with this. We've used this a lot throughout this term, but when you start off with the actual nucleus, the dense solid nucleus, in there you have your protons and your neutrons, and then you have your electrons on the outside. So remember that the mass assigned to a proton is 1 AMU, and a neutron is 1 AMU. So that is how carbon-12 is carbon-12. It has 6 Protons, 6 neutrons, so that's 6 AMU plus 6 AMU, and that's how you get the 12 atomic mass units. Charge is said to be 1 positive unit for proton, no charge for a neutron, and then the electron. The electron is 1 negative charge. And remember, the electrons are on the outside, and we're going to get into that electron configuration here in a second. But please remember, why is electron's mass said to be insignificant? It's 1/2000th. Actually, it's 1/1840th. But close to 1/2000th the mass of a proton or neutron. That's why it's negligible. Electron configuration. Hopefully this really rings a bell with you. You have your periodic table broke down into your S group over here. You have your P group. You have your D group. And then you have down here your F group. Now, we didn't use the F group a lot, and you probably won't have to worry so much on that. But having to put them together, remember the highest energy levels are the S and the P. Highest energy levels are S and P. Your D falls back 1 energy level. That's why you see it goes on the 4th energy level here. So you have your 1, 2, 3, 4, 5, 6, and 7. That's why D falls 1 and F falls 2. So hopefully that all comes back to you. So let's look at a few examples of putting together. And if you remember, we tested on this, and this was actually a fairly high miss question, because I think that we forgot, for the most part, that we still have to know how to put electron configurations together. So here are some common ones. So you have your 1s2, 2s2, 2p2 carbon. You go over to sodium, 1s2, 2s2, 2p6, 3s1. Remember over here, this side is showing, and I'm just going to put a little box around it. That is the kernel method. That's the shorthand notation using the noble gas that came before it. Also, please remember, you may have to show the electrons. So let's talk about carbon first. So let's look at this right here. If you had to write the electron configuration, you get your periodic table and you just simply look down at 1s2, 2s2, 2p2. And that's what you see written here. What if you had to draw it? So let's just refresh our memory on this. So first off, please remember that S orbitals are circular and they are 1. It's represented by 1 orbital. Then you have your P, they're dumbbell, and 1, 2, 3. Then you have your D, they are double dumbbell, and they're 5. 1, 2, 3, 4, 5. And then you have your F group, and that is the cloud formation, and that is 7. 1, 2, 3, 4, 5, 6, 7. That's just a quick reference on that. So if we look at carbon, so let's look at carbon and we'll look at sodium. So if I look at carbon, I have 1s, I have 2s, and then I have 2p, 1, 2, 3. So I have a total of, if I look at my periodic table, I have 6 electrons. So I have 1, 2, 3, 4, 5, 6. So the last electron has an upspin. So it has, it's both outer electrons are upspin. And we could get into hybrid orbitals, and we're going to do that in another lesson. But hybrid orbitals, we have hybridization take place here, and that's how you can get the 4 bonds. And we'll look at that in a little more detail in another lesson. Let's also look at, let's just jump right over here to sodium. So we have sodium with 1s. So I come over here and I go 1s. And then I have 2s. And then I have my 2p. 1, 2, 3. And then I have my 3s. And I could draw this. So first off, finding my sodium, I have 11 electrons. So I just start filling them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Its last in the 3s is an upspin. And we can talk about it's going to lose that 3s so it can be more stable. And that way it can be configured like neon, but we'll do that a little bit later on. But nevertheless, hopefully this all comes back to you. We've done this a lot. We've had them on some of our tests, but that is electron configuration, both written, shorthand, and drawn. Coulomb's law. So here we have this equation. So please remember about Coulomb. We use Coulomb's law for justification of attraction and repulsion forces. So Coulomb's law relates 2-point charges and the distance separating them. So we didn't have to use this formula. So here we have our force, whether it's a force of attraction or repulsion. Remember, we use it for either one. We have our K value, which is Coulomb's constant, and then you have Q1 and Q2, which are the actual charges that the two atoms that are being related, and then you have here their distance apart, and that is the radius of each of them from each other. So the radius of the distance apart, and that is in picometers. So we're talking about very small numbers here. So there is a force of attraction. This is still using Coulomb's law of unlike charges. So here you see the of unlike charges are attraction. So here you see them coming together. You have the plus and you have the minus, and then there's force of repulsion. That positive and negative, they don't want to be put next to each other. So if you force them, you can actually calculate the charge. And here's our formula again. And you don't have to use the formula, you just have to use that as justification. Q1 and Q2 are the electrical charges of the two atoms, and R is the distance between the charges, and that's in picometers. And then K, it says, what is K? Well, K is Coulomb's constant. All right, now we're at photoelectron spectroscopy. Hopefully, just by taking a look at this, it rings a bell and you remember the process. So when you look at this, the closer you are, the higher to the left, the higher the energy. And here we're in megajoules, which is more than a kilojoule, a megajoule per mole. So when you look at here, this is 151. This is really, really strong attraction force here. That's the energy that's holding it in place. So to remove that would be extremely, extremely difficult. When you come all the way out here, you see 58.58, not so much. It's much, much less and easier to remove. We'll talk more about that. But when you look at this, the way that you read this is the highest energy level is going to be, and this is where it gets a little tricky when you're thinking about this, the highest energy level is all the way out here, even though it is the least binding energy. It is actually further out away from the nucleus. The nucleus is said to be basically right here, and these are how close they are. So when you look at this, you have the 1s, and you can count them, 2 electrons. So this is 1s2. Come out here is 2s2. This here is 2p, and you can count 1, 2, 3, 4, 5, 6. And you come out to here, you have 3s2, and then here 1. 3p1. So what element are we looking at here? So we have 1s2, 2s2, 2p6. So get our periodic table, and we can look at this periodic table, and we are looking at aluminum. So this here is aluminum. So that's how you read and look at these charts. Hopefully you remember doing that. We did quite a number of these charts earlier in the term. Now, this can also show us why, in fact, does aluminum become a +3 charge. When you look at this, these two right here and this one electron have low binding energy, which means that it can be removed. The ionization energy, it can allow them to remove, and that's why it becomes a 3+ charge. Why can't it become 4+? Well, look at how significantly higher that ionization energy would be, and it's not going to happen. But those 3 electrons on the outer, it can lose, the aluminum can lose that, be configured like neon, and be much stabler, much more stable. Here's chlorine. So let's just take a quick look at it. Same thing here, we're dealing with megajoules, and we could actually count. This one doesn't give us the little lines, but we can look at and understand what we have here. We have 2, we have 2, we have 2. Here we have 6 electrons, and here we would have 5 electrons. And this ends up being chlorine. So you have 1 S2, 2 S2, 2 P6, 3 S2, and then 3P5. When you talk about 3P5, 1, 2, 3, 4, 5, and that is chlorine, Cl. And when you see what does chlorine do to get stable, it steals an electron. Well, look at here, you're at about 2 megajoules to remove an electron, and that's not going to happen. It's going to take, it's much easier to gain one and become stable like argon in this case. And that's why chlorine will get a 1- charge. So that is photoelectron spectroscopy. Hopefully you remember that process of looking. Whether it gives you the little lines to count or not, you can still match it up and determine which element it's talking about. Here's probably the biggest portion of Unit 1 is trends, and we're going to spend just a few seconds and talk about that. Well, electronegativity, our first one listed here. Please remember electronegativity. As you move up to the right corner, remember, electronegativity does not include, talk about the electronegativity, it doesn't include those noble gases. Typically, most Pauling scales, that's your electronegativity. It doesn't have those. So some of them can have a Pauling number, but for the most part, you will not find that chart. But electronegativity, with fluorine being the highest electronegative and coming all the way down to cesium being the least electronegative, remember the trend. It increases as you move across and decreases as you move down. So in other words, as you move up and to the right, it increases. As you move down and to the left, it decreases. We talked about ionization energy just on the last slide. So the ionization energy, remember what ionization is. Ionization is the energy required to remove an outer electron. The energy required to remove an electron is ionization. When we talk about electronegativity, it is the ability to attract, an atom's ability to attract electrons to itself when it's bonded. That's electronegativity. So we talked about that trend. Now ionization is going to follow the same trend. The energy to remove will increase as you move across to the right, and it will decrease as you move down a group. So if you talk about fluorine, the ionization energy of fluorine is tremendous. I mean, it's not going to have an electron removed because you can't. When you come down to cesium, it's easily removed, and that's why that group 1 metals are so reactive, is because they're to the far left and they can have that outer electron removed very quickly. Now, when we talk about that ionization energy, please also remember there's ionization energy 1, ionization energy 2, ionization energy 3, and as you remove more electrons, the ionization energy becomes higher and higher. So keep that in mind. Now, atomic radius. So that has everything to do with the nuclear charge and the number of electrons that are around it. So when we talk about the atomic radius increases as you move down a family group. It increases, and as you move across, it decreases. So think about, why does it decrease as you move across? So if you picked period 4, and that's the one that has potassium on it. So we'd be talking about right here. If we pick this is K right here. We pick that group right there, that period going across, and we look. we are not going further shells. There are no more shells going out, but we're adding more nuclear charge because every time we go one to the right, we're adding another proton. That's why it decreases, because the more protons you're adding and you're not getting any more layers of electrons, it's going to be able to pull those in slightly more. So when you talk about the radius, it decreases as you go to the right and it increases as you go down. The nuclear charge, well, that's the number of protons. It increases as you go to the right and increases as you go down. Because as you go down into different groups, now you're getting more and more protons in the nucleus. Now shielding, the last concept here, shielding. The shielding increases as you go down. Why does shielding increase as you go down? Think about that for a second. You are adding levels, layers. You're going to 1s, then the 2, then the 3, then the 4, then the 5. So you're adding layers. So the shielding is increasing. But as you move across, you are not adding more layers. You're adding more electrons, yes, but they're in the same level. So therefore, it is not adding any more shielding effect. So you have the overall nuclear charge, the number of protons that are attracting those electrons and hold them in. You may be adding more electrons, but it's all in the same layer. So it is being held in with constant force, because even though you're adding more electrons, you're also adding more protons as you move across. So the shielding is said to be constant. So hopefully these trends, you remember them. They're really important, and they help you apply many different principles and properties as we went through other units in this AP Chem class. Here's our electron dot structure. I'm not going to belabor this. We know how to do electron dot structure. We know how to draw them. We space them out. This is the precursor to Lewis structures, which we're going to talk about in the next video virtual lesson, is Lewis structure, and that's unit 2, and we've got to be able to draw the Lewis structures. But this is the precursor to learn how to do it. And this is a nice slide here. It shows you the exact format. You have to put 2 on either, when you have 2 on either side, just like you see here. The only exception is helium. Helium must be placed together like that because it's stable. And that is our octet rule violation. But this is how you determine and show all of them, whether they're in their normal state or if they are an ion. So if we just refresh that, we have beryllium, 1, 2. Remember, you can count them or you can look up at the group number, and the group number tells you how many valence electrons. These are your valence electrons. Remember, your valence electrons are the outermost electrons, and those are the ones that are involved, for the most part, are involved in bonding. So beryllium, that's its neutral state. If you talk about its cation state, it loses them and becomes Be2+. If you had sodium, let's come over here. We have Na, and you have 1, and that is neutral form, and you have Na1+. Remember, metals and nonmetals are shown differently. So if I come over here to oxygen, you see oxygen listed right here for us. And oxygen has 1, 2, 3, 4, 5, 6. So I can go 1, 2, 3, 4, 5, and I have my 6th one right there. So that's neutral. If I have my oxygen, I have to show a full octet and the 2- on the outside. So that's the difference between showing an electron dot representing a metal and a nonmetal. On a nonmetal, I do not show any electrons in the valence shell when it is a cation. But on a nonmetal, I must show the full octet and then the charge associated, and that's how the difference is there between the metals and the nonmetals, and oxygen shows that there for you. And we've come to the last slide here. This is ionic compounds and ions. I talked a little bit about ions and how you represent them. So please remember, metals tend to lose their electrons and become positively charged. Nonmetals gain, become negative charge, and become anions. We're going to get into naming and that in the next lesson, but we're pretty familiar with that already. When you talk about an ionic compound, it is the electrostatic charge attraction between a cation and an anion. And it is a very strong bond, very strong bond. Takes a tremendous amount of energy in order to dissociate that bond. But here we have a nice representation of it. Sodium loses that one electron in the 3s. Chlorine picks it up, becomes configured like argon, and then what happens is you get a positive and a negative charge. They counteract each other. Remember, ionic compounds never have an overall charge. They're always neutral. And in this case here, we have the sodium and the chloride bonding together. And we could talk about the unit cells, we could talk about the shapes and all those things, but nevertheless, it forms a crystalline structure, a solid crystalline structure. And that is basically a wrap on Unit 1. This is your Unit 1 review. Hopefully some of that came back to you. That is it. Hopefully you can work through the AP classroom quiz that's due tomorrow by 11:59 p.m. and then be able to read and work through Chapter 5 in your 5 Steps to a 5 workbook that you got at Christmas time. I do ask that you write out your answers. I know the answers are right there in the book, but it's on a different page. So don't cheat yourself. Do the answers. If you missed it, you missed it. I'm giving you completion grade on that particular assignment. AP classroom quizzes are graded. These 5 Step to a 5 problems that I'm assigning you are going to be completion grades. So work through them. By me looking through the answers that are submitted can give me feedback on which things I need to spend more time on. So hope you enjoyed the virtual lesson. Any questions, shoot me an email. Thank you. Go in peace.